Okay, thank you everybody who joined this webinar. And I want to thank also to all of the MindWare team who did a lot of effort to join here and make this webinar for us. And the speaker for today will be Jay. He is the Director of Sales and Training in MindWare. And I hope you'll enjoy it. If you're watching the recording or if you're here live, please feel free to join and participate. And Jay, the stage is yours.
All right, Ite, thank you. Appreciate it. And as you just said, my name is Jay Schmidt. I am the Director of Training Sales here at MindWare, and I'm going to be presenting the webinar for you all today. Just a couple quick notes before we get started. We have some helpful slides here on just making sure that you can organize Zoom how you want it. So if you have any sort of audio issues, we have a little carrot right there, and sometimes a monitor can be connected to speakers. So if you click that little up carrot there, you can change that over to your normal speakers. Questions, please ask them as soon as you have them. We have a panel here of people that will be collecting those questions, confirming that they've received your question, and then putting them into a queue. So the idea would be that we're going to be presenting content for about an hour, and then an additional 30 minutes after that, we'll actually be taking the questions that you asked and answering them live for everybody. For those questions that we don't get answered during the webinar, then we will follow up individually with those and address them afterwards. And a couple things as well before we go into this a little bit more is we also have a post-webinar survey that we would appreciate you all filling out. In so doing that, you will also receive a certificate of completion for the webinar. So please be on the lookout for that. Okay, next thing I wanted to show you to before we get started here is just our support site. So you can see here, it's support.mindwaretech.com. It's a very nice user interface where we can download software that you can see here near the bottom left. There's no user login, so it's very easy to access. We can also create support cases if you have any sort of issues with some sort of technical issues that you might be having. We also have one-on-one training. So if we go over to the MindWare training section, you'll see various options for remote training, which works in a similar way as what we're having here with Zoom, where we can actually go through everything of data acquisition to analysis with you. If you've already paid for training with MindWare, we always have the complimentary options available to you in 1 hour blocks. So please do check those things out as well. Okay, so next thing is at the bottom of all our pages here, including the last one, you'll see that there is a subscription thing here. Certainly there's different things you can subscribe for. The quarterly newsletter kind of letting us know what we're doing. News events such as our in-person psychophysiology seminar and workshop. We're actually holding that in Columbus, Ohio here in August. I don't know how many people from this webinar will actually be able to attend here all the way to the States, but if it is something that you're interested in or potentially have a collaborator, please you can check the bottom of our webinar announcements. It's also on the bottom of our emails. You can go to our main site or the support site. You'll see some things for that. And you can see here at the bottom right, we also have the training events, and that'll show you that seminar information. Great, and then clicking on that top right training guides here, you can actually see when going into here, we have a nice amount of articles here that you can go through just the introductory, what is skin conductance, all the way through data editing, data collection tips, reference materials, all that can be viewed there. Now I just want to walk you through a tip or maybe an ideal or typical data collection analysis workflow we have here. So what we see here on the left is the data collection device. So this is our MindWare Mobile. It can pair with this audio video recording field laboratory integration platform, or FLIP is what we call it for short, to collect all the sort of audio, video, and physiological data. We can also pair this with eye trackers, such as Tobii eye trackers. And then essentially we have two analysis pipelines from here, one in which we might be actually using the audio video to code for affective behavior in a software such as Notice Observer. In that, what we'll do is we'll take the videos into Observer. we'll go ahead and create our event marking scheme due to our study. In so doing those event markers, you create an event file, and that event file is directly loaded into the MindWare analysis software. So we can actually do that synchrony offline and actually look at those events and what was the physiological connection to those events that we put into Null's Observer, for instance. In tandem with that, you can also take the eye tracking data, analyze this in something like Tobii ProLab, and then which those videos can also be imported into mine where you can actually look at the eye tracking as it occurs with physiology for some sort of synchrony between the two. We can also directly read the events that might be present in your Tobii eye tracking data. So just something to think about if you have anything in these realms and you wanted to add one or the other, certainly reach out to us and we can assist you with that. Um, Another quick slide here is just another integration that's brand new that we just like to highlight for everybody is we now have a cable that'll integrate the CareScape V100 into BioLab. This is a very standard clinical and research grade monitor, and we can actually now control it from our software, starting and stopping measurements, actually receiving the timestamp blood pressure and the mean arterial pressure within our file. So nice update there. Last thing I wanted to kind of show you all as far as a product, we actually have a study compiler here. So for those of you that have our analysis software, you're actually using it, you're putting this into a huge aggregate of all these different files after you output from our analysis. And this is a new application we have which actually allows you to load them all in batch or individually, set these different epochs and criteria based off the data, and then output it to a single file that's ready for your stats package, as you can see here, commonly used in SPSS, SAS, and R. And then just if anyone is interested in as well, we certainly, if you're here to look how to analyze your own data, you have our software, great. Another alternative to this is you can actually send us your data, certainly the de-identified data. We'll go through and meet with you on exactly the study paradigms that you have set up, and then we'll go ahead and actually have one of our trained data analysis experts go through and actually clean the data with comprehensive notes on exactly why a decision was made. And then you'll actually get a project completion report where we'll meet with you again, some analysis and preliminary results, interpretations, all that kind of stuff. So if you're interested in this, again, please reach out to sales if we can help you with that. Okay, now going into the actual content here for skin conductance, just a couple things that are helpful. File storage, usually keeping a unique folder for every participant is a great idea. Certainly if you had the study compiler, this isn't as mandatory of a organization because it can individually find all those things. This is just a helpful way in which we can separate data in case we don't have that. A couple different file types you're going to see are the .mwx and .mwy. So these are the raw data is the MWX. It's an uneditable file. And then we also have the MWI, which is an index file. So when we're actually loading the data after we acquire them, our analysis is only going to be looking for the index file, which essentially will extract information from the raw data, which is the MWX, without making any edits to it or any changes. So this allows us to ensure that we always have our raw data preserved. If anything were to happen to the files, let's say that Windows crashes or something occurs in your PC, such as a power outage, it is always possible that any file in Windows that you're actively loading can be corrupted. Thus, if we were loading MWI and anything occurred to this, we can simply just delete this and recreate that file later on. So that's why we sort of have this tandem companion file structure. If you're ever going to be saving, sending the data to somebody, pushing up to the cloud, always include both of those files. There's also user preferences. This is going to keep things such as channel mapping, which I'll show you in a little bit, in different settings. So this will be created once we actually open a file and make some edits, and then it'll just automatically be loaded every time we reload that file. So something that you really don't have to pay too much attention to. It can kind of just exist in the background, but that's what that file does. And then finally, we have an edited data file, which in this case are going to be either an EDH2, that's for our heart rate variability analysis. We have EDI2 for impedance, And then as you might guess, we have an EDH2 here for skin conductance. So just different edit files that you may have if you're collecting our three most common measures. And these are actually things that we're going to want to load. If we're cleaning a data file, we want to reinspect it, we're going to want to make sure that we load those EDH files, which I will show you in just a minute. Great. Okay. So moving on from here, I just want to go over some quick waveform components here of skin conductance, skin conductance responses, levels, and just so we can define those things when we're actually looking at analysis, this is helpful. So at the top left here, we're talking about latency. So if we imagine that there is something like a stimulus response that occurs, let's say at time 0, this can be sort of in a real world application. We can create some sort of startle response, let's say, to the participant, and we want to know from the actual onset of that stimuli. Let's say it's visual, they're working with the computer screen. It's acoustical, we're actually using some sort of sound. To actually, elicit some sort of response. It can be in a couple different applications, could also be in electrical stimulation. Let's just say that all of these things that might occur at this time 0 point, there is a latency. There is sort of just an anatomical, physiological latency between when a stimuli occurs and when we can actually see a skin conductance response. So skin conductance responses are spontaneous activation of the sympathetic nervous system. And so from that point to when we actually see the response is usually about 1 to 3 seconds. That's just how long the sympathetic activation normally occurs throughout the body. So there's a little bit of error bars on that, but that's kind of the window we're looking at. So essentially here, we want to identify and characterize this latency, and then that'll allow us to determine the windows as to when a rise can occur. This is a helpful thing so that we can sort of differentiate movement artifacts and respiration artifacts from actual legitimate skin conductance responses. If it's not physiologically possible for us to see activation within this latency period, then we should ignore that. And that's what we're going to do here. So again, this is normally 1 to 3 second window here. I would recommend that same window. But that sort of maximum window is sometimes extended up to 4 seconds in some studies. So the trough of the skin conductance response, this is actually the sort of lowest point here before it occurs. This is detected by first, once we actually find the peak of this and it starts to drop down, we know that's the sort of peak of the skin conductance response. We can then track back to the beginning or onset of that response and then put that trough location. The next thing that we're going to be looking at is a SCR peak. So there's just right up here. It's just the tallest point of that response. And yeah, we can kind of get the amplitude of the response as well. So now that we know the baseline or the trough period, and then we have the highest point here, we can actually see the amplitude of that actual response. Last thing I want to talk about here, as far as this component of it all, is the halfway recovery time or just half recovery time. So this is the minimum amount of time until we can actually detect one skin conductance response from another. Essentially, there are things such as these compounding SCRs in which we see one response and then another one that piggybacks right off the top of it before it goes down to its normal baseline level. So let's just say this is their normal level that occurs here before the onset. Before this one actually falls back down, we could see another response. And we'll see plenty of examples of this when I actually show the software, but the half recovery time is important such that we're tracking when another SCR could occur. And this can be done in a couple different ways. We can actually look at the rise time and get that information to let us know what would occur here. But the sort of half recovery time in general, and the rise time are extremely highly correlated. They're sort of redundant in a lot of cases. So we usually prefer the half recovery time because it's a little easier to track. But if you've seen some sort of literature in which you're using that rise time to detect sort of the ability or the second SCR that could occur, how long it might take until it goes back down to its normal baseline level. that's perfectly fine as well. But as far as MindWare is concerned, we're using the half recovery time to detect the sort of ending point of that SCR. Okay, great. And then a couple things I want to just talk about with tonic versus phasic period. So tonic level here, this is a good approximation, as it says here, of the data, and it can change over time. And what we'll see here is with tonic period is instances in which we're not responding. So what we're going to do is we're going to define windows that we've seen before. We have our trough here, we have our peak, and then we have our half recovery point. And so all the time spent from the trough to the half recovery point, this is known as the phasic period. So this is that sort of sympathetic activation. And then outside of these windows, so from this half recovery point to the next trough, this is all going to be our tonic period. So essentially, there aren't any skin conductance responses occurring. And yeah, it can just be a helpful guide here on the sort of overall activation within a time period. So two things to look at within there. So the mean skin conductance level, those are going to be adjusted, by that phasic activity, and then the sort of tonic period being that overall, and also including that time in which we're not seeing any of those spontaneous sympathetic contributions or those SCRs. So yeah, sort of two ways to look at both things, and look, sort of combining it all will give us our entire period here. So. If we look at the actual time scale here, we have 240 seconds to 300, so we're actually looking at a 60-second window. But the actual period in which the sort of tonic period is 37 seconds. So thus, we have about 23 seconds in which the phasic periods occur for these 5 different responses you see here. Okay, great. And next thing here is we're going to just looking at a rolling filter. So I'm going to show you this in the actual calibration settings. We're also going to see it um, when we're actually looking at the data here. But the rolling filter is something that we definitely recommend, especially if you're going to be looking at skin conductance responses. Um, but in either case, it's a nice way to actually smooth the data out and remove any sort of high frequency interference, noise in the signal, and potentially any sort of motion artifact. So for those of you that collected these data, um, one of the sort of issues with it, or potential confounds, is just that it's very susceptible to movement artifact, right? If we're collecting this from the hands, the fingers, or the bottom of the feet, those are the most common locations. Every time that essentially they move that part of their body, we can see some of these movement artifacts that create these sort of jagged lines that we're seeing here. With skin conductance, we really should see very smooth, sort of rolling lines in a lot of cases, unless, again, we have some sort of high frequency noise or movement or something with the data quality. But what we should see here is this sort of smoothed out rolling filter that we see here in the bottom right. So what this is doing essentially is moving through with the window, and it's connecting the points through here in some sort of bin. So I'll show you this in just a second when we're looking at the rolling filter at the bottom here. So looking at the actual calibration settings in the application, I have just a couple screenshots of this to explain some things. So the segment length and sort of the microsiemens threshold. So the actual thing that we're going to be looking at here is US, or it's the sort of indication for microsiemen. This is the level at which point we actually say that this could be a skin conductance response. So again, there are going to be small changes that you see here, even within the application itself. So there's tiny little bumps here, and why these are not being included as different skin conductor responses is because their amplitude is not that 0.05 or above. So any of these very small changes, even if we're using here, are going to be in a lot of cases removed by having that rolling filter on. And when we're doing that, then it's nice to look at that threshold. So this is usually 0.05. In the literature, you'll also see that this is sometimes 0.03. Certainly you can reference a different article if you're looking for a study replication, but in most cases, that 0.05 is the most commonly reported. The event-related SCRs and the sort of min and max here. So Yeah, the min is normally 1 second here. This is, again, just due to sort of sympathetic activation periods. It's not really proper to think about anything less than a second just because of that sort of time that it takes for that activation. But the skin conductance response max that you see there is usually about 3 seconds and can also be used as 4 seconds. So what these are doing, again, is that sort of window that we were looking at before. I'll jump back just a couple slides here. So that point at which we actually see that stimuli until we actually this latency period here. So this would be our 1 second window as sort of that minimum, and then the 3 second window or 4 second window being over here at that recovery point. So again, that's usually done in the 1 to 3 or 1 to 4 second range, but as a default here at MindWare we do 1 to 3. Okay. The other component here, I guess, that maybe I didn't harp on enough is just the fact that these are event related. So in the cases that we saw on the previous slide where we had that red stimuli mark, that would actually be events that were created in the file. So let's say that we have a stimulus presentation program such as SuperLab or ePrime, maybe we're using PsychoPy. The idea would be that, let's say they're watching a video or something within one of those programs, and pre-programmed, we have these different markers that say something like, here's the onset of the video, here's the closing of the video, and then some sort of markers within the video of when, let's say, an emotional uh, component of the video is presented and it's supposed to elicit some sort of response. So at that point, that's an event at which we could say, let me see what the change in skin conductance is following that marker. Is there some sort of emotional, response that's elicited by that event? And this is what allows us to kind of capture and correlate the actual stimuli within the protocol to the skin conductance response. So those are ER, SCR, that means event-related skin conductance responses. So if we see skin conductance responses that occur in the absence of any sort of stimuli, then those are going to be calculated as non-specific SCRs, so NS. And we'll see those in just a little bit. Okay, last thing is I want to talk about the calibration page here, and then we can shortly jump into the actual analysis and the our application. Is we have two different things. We have the calculation method. So as we see here, this is set to currently as entire. If we drop that window down to interval, then the interval period will light up here to the right of it, and we can choose different windows within the actual segments to look at. So again, let's go back to the example in which we had 60 seconds of data. I think it was 240 to 300. So in that 60-second window, we are going to calculate all these different statistics, such as the SCRs that occur, whether they're event-related or non-specific, the tonic period, the skin conductance level. All of those things are going to be calculated on that initial window, let's say that 60 seconds that we defined. This right here, if we turn to intervals, lets us do an additional layer to that. So it actually says that we can break it up into individual periods, and then we can get some basic statistics on that, such as the number of skin conductance responses that occurred in that period, and also the level. So if we were concerned about some sort of non-stationaries in data, or we want to track that second by second change in level changes, then this is a nice way to kind of get that done. So another thing you could do other than second by second changes would be to break that up into those 3 or 4 second windows and move through the data in that way. Can be helpful, especially if we're not doing event-related SCRs and we're just wanting to know an entire count of all of the ones, the sort of non-specific ones that occur. And then last thing we see here, it's not going to focus on it too much, but respiration is simple to use. So in a lot of cases, when we're looking to report on event-related skin conductance responses, we're going to want to also collect a synchronized respiration signal. That is because with those skin conductance responses, they can be elicited by motion artifact. It normally looks quite a bit different because it's sort of jagged, as we saw before. But the other thing that looks exactly the same to a sort of psychologically driven skin conductance response is a very deep breath. So if someone takes a deep breath, maybe it could be from a startle, if that's part of the protocol, or from talking very long, and then you take a deep breath afterwards. A sneeze, for instance, can elicit a deep breath afterwards. Those different breathing patterns can actually create a skin conductance response. And so by having the respiration signal in synchrony and collected with the skin conductance data, we can differentiate those and actually make some sort of editing or manipulation to the data to remove those respiration-driven skin conductance responses. Okay, the rolling filter here that we see is the last section I want to show within the calibration settings. And what this is going to do is thinking about some sort of smoothing the data out so that we don't see any of those sort of high frequency noise or motion artifacts within the data set. I'm going to show you the example just in the next slide here, but a nice thing to have on this is to always have it on, would be our recommendation, like I said before, especially if we're looking to report on skin conductance responses. A nice starting point for this sort of block size is 500. So the first idea or recommendation I would give is that you match the sampling frequency of the device that you use to collect the data. So let's say that your sampling frequency was 250 hertz, where it records 250 samples per second. Or in this case, where it's 500 hertz device, where it's again collecting 500 samples per second, we're going to want that block size to match that sampling rate. That'll help us ensure that we're not seeing any sort of phase shifts in the data. So yeah, anyways, this was collected with the MindWare Mobile, which is 500 hertz, so we're going to set that to 500. Okay. Great. So the electrodermal activity, just rules and recommendations. There's not a lot here. Honestly, it's, in a lot of cases similar to a measure such as EMG, electromyography, where, in a lot of cases the signal is hard to interpret because these points that we're talking about, these sort of fiducial markers of when does that trough occur, when is the peak, and then how do I make edits from there? It's honestly a little bit open to interpretation throughout the literature. Our main focus and recommendations is that consistency within the study. If we can define how we're editing these data and be consistent through it, especially if we have multiple raters, that's usually what we're looking for. Certainly referencing some literature with general standards is helpful, but you'll see in such that the interpretations can be a little bit more ambiguous. So keeping some standards here that are just our general sort of rule of thumbs and recommendations. Usually segments are about 30 to seconds. This is just to measure other measures that you might be collecting. So let's imagine that you're doing ECG collection and impedance collection, and in those windows we're setting 30 seconds. Then normally researchers will just match the segment lengths for that same reason. Certainly not mandatory. You can do skin conductance response on as little as 10-second windows. This can technically be done in smaller windows, but we don't usually recommend it. You can sort of understand from a point of looking at the latency of the skin conductance responses and the total sort of recovery time. We could certainly see a response that occurs in that 3 to 4 second window, and then you have some unknown amount of time until it recovers, so it sort of reaches its half recovery point. So um, with a little bit of variance there and some high, error bars there, 10-second window is usually fine to go with, but yeah, again, normally 30 to 60 seconds is what's actually occurs. And then it's sort of extrapolation data retention. So I'll show you in just a little bit what we're talking about here with this far extending the signal. So in some cases, we can see something like a signal dropout, where potentially one of the sensors is, let's say, coming off of their hand temporarily. Normally what we'll see is the signal go from its sort of mean baseline and drop down to maybe something like 0 or negative. And you see this sharp line. So as I said before, this usually shouldn't be possible, and so this is a way in which we can use an extender to essentially say this is a motion artifact or this is, an electrode popping off. But we want to try to normalize the data as much as possible to try to retain that segment. Try to do this less than 40% of a segment. We have that sort of rule of trying to retain at least 50 or 60% of data within a segment. With skin conductance in particular, the skin conductance level, or SCL, if you're looking to report on that, normally extending data for something like up to 40% of a segment is fine because the level shouldn't change that much throughout there. However, if you are looking to report on skin conductance responses, then we need to be very careful and be thoughtful about how we're going to be using this extension feature. If it's going to simply remove some unknown amount of SCRs within a segment, well, this is going to be, something where in which we're reducing or skewing the data to report that we're actually seeing less SCRs than we did in reality. So keeping that consideration, extending these is, again, normally a recommendation only if we're doing skin conductance level, but we'll kind of see what I'm talking about in just a little bit. Okay, so before we get going further into the Q&A component, I do have the analysis software open here, and yeah, I would love to kind of walk everyone through this, and we can see a little bit of the actual editing component of this, which we've all been waiting for about 40 minutes, and then we can go ahead and enter into the Q&A portion. So I've already loaded this first file. I will certainly go through and just briefly show the opening and editing component of it all. As far as the different components here of time and events and multi-event, I'm going to just briefly cover those. Um, but yeah, there's certainly other resources within our support site. If we go to that training guide, there's the a three-part webinar on the actual acquisition of the signals, and then in there it'll actually go through the um, different settings in this as well. So another feature here that I would like to just explain to everybody, if you're ever in question about something, what should this be set to? What does this mean? What you can do in a lot of cases is just hover over that title or the box, and then while you're hovered over it, just hit the Control H, and that'll actually load the manual, and it'll go to the part of the manual that covers what your mouse is hovered over. So it's a very nice sort of smart feature there to get to the information as soon as possible. But anyways, going to the calibration settings, as we saw before, we have the override gain settings. If you're using a MindWare device to collect the data, you don't have to worry about it. It'll be grayed out. If we do have a different acquisition hardware and system, then you will want to, in most cases, override the gain settings and make sure that it's a 1-to-1 for each microsiemen per volt. So in MindWare, we analyze and collect everything in volts. So in a software that doesn't do that, we want to know that conversion rate. You can usually just check out the manual of the hardware device that you have and look at and see how those microsiemens were recorded, right, in volts or in something else, and then create that conversion. Okay, so I've go ahead and set up my calibration settings to mostly what we saw before, as sort of the default settings. In this case, I do not have a respiration signal within this file, so this is going to be set to none. And just to sort of visualize the sort of rolling filter and block size here to sort of understand what that block size should be set to, we can always go up to File and then look at our file info. This should actually show us what the sampling frequency is for all these different waveforms. And we see our galvanic skin conductance, or GSC, was actually sampled at 1,000 in this case. So then, as I said before, we want to set that block size to 1,000 as a good starting point. And then we can kind of go from there. So I'm going to actually go into the analysis screen, and we can start to look at some of these data sets here. So in this first example, we do have a somewhat smooth line. We see some sharpness in that, but this can occur when we're really zoomed in, for instance. So the analysis screens are going to auto scale. They're going to zoom in or out to show you the entire amplitude of the signal. So from this sort of starting point here in quadrant 2 down to 4. And when it does that, if there isn't a lot of activation, which we can see in this case, then the waveform is going to look a little bit messier, of course, because we're super zoomed in. So why we're not seeing a lot of change is actually because we're actually looking at the Y-scale here. We're very zoomed in sort of to this little range of 3 microsiemens. Our entire sort of amplitude of this segment here is 3.29 down to 3.12. So remember, the skin conductance response minimums is 0.05 and above. So if we actually go into this editor here, we can actually see by defining our windows here, if this is our trough of that point to when this peak occurs here, the delta between the y or the x, if we look up here, that is the absolute sort of time between them and or amplitude between them. And so what we can see here, this is 0.02. So we needed 0.05 or above to be marked as a SCR. So this is why this one does not have our nice little colored circles here of when the trough, peak, and half recovery point occur. So that is why this signal, it looks a little bit normal to what we're seeing here with these sort of slow moving rolling hills. But because we don't actually see that much of a range change within the SCRs, there isn't anything to be identified. So if you ever see this, don't think that the data are invalid or there's something wrong with the analysis software. You can certainly use that tool that I just showed you of editing the peaks and moving those cursors along to see why you might not be seeing that change if it's just not obvious to you over here on the Y scale. Okay, so I'm gonna move through this to the second segment here. So this is another thing I want to show that can occur with the analysis, especially during something like a baseline or a recovery after a stress induction task. What we can see is that there's actually this sort of phenomenon of this sympathetic withdrawal. So in these cases, we're not seeing any activation in those eccrine sweat glands at the point of your sensor location. And this is, a very normal thing to see, a sort of straight line going for quadrant 2 to 4. And again, this doesn't mean that there's something wrong with the data. We see we're in a normative range, and yeah, everything's great here. It's just something to be cognizant of when you see these. It doesn't mean that anything's wrong necessarily. We just, again, that participant is not expressing any sort of sympathetic activation. Great. As far as ranges go, I just kind of briefly touched this here. So, as far as normative ranges for participants, this is going to be between 2 and 20 microsiemens. As far as a reportable range, what we normally see in literature is something around zero point 0.5 or 1/2 of a microsiemen, all the way up to 35. So, if we're seeing something that is higher than 35, normally, what we find is that's indicative of putting the wrong type of sensors on. So if we actually use the ECG sensors, those are a 7% silver chloride on average. And then skin conductance sensors, or the paste that's used in them, is about 0.5. It's sort of the conductance trying to replicate that of sweat. So if we're using the wrong type of electrolyte, we can amplify that signal by some unknown amount. Um, and yeah, so usually that's the case with that. I mean, certainly you can be observing someone that has something like hyperhidrosis, right? They're just extremely sweaty, which they could exceed that bound. Um, and then as far as low levels, when we see something on below 2 or especially below 0.5, that's usually indicative of something like dehydration. That's kind of the number one reason why we might see that. The other might be that the sensors are dried out. So if the gel is dried out, that's another reason why we might see a very low level. And then you can have other things such as different drug interactions that the participants might be having, age, race, everything. It can change the sort of dermis and the different levels of the amount of sweat that we're seeing. So another thing is sort of standardizing these between participants is to look at the overall range for a participant, and then comparing that to the range of other participants within a study. So not just looking at the overall mean skin conductance and sort of averaging across for between a subject analysis, but actually defining that range up front, normalizing the data, such as we're dividing it by its normal amount, and then we can kind of see a normative range for everybody. Great. So anyways, we're just kind of moving along here, and we don't see a lot of activation until we're here on segment 5. So finally, we're looking at a very small window, so just kind of keep in mind here. This is why we're sort of zoomed in again, is we're only looking at 240 to 264 seconds, so only about 24 seconds there. And so, but we have identified some components here. We have our trough point before it starts to rise up. We see that the rise peak here is being identified. And then We don't actually have an X, as you see here, so there isn't a half recovery point because we do have a second response occurring. So this is perfectly fine as well. So we have the trough and peak, no recovery, because again, we have a sort of second compounding skin conductance response. So here's another trough, here's another peak. And this one does have a half recovery point that's being identified there. Unfortunately, what occurs after this is something similar to what I was talking about before, where we see that very immediate drop off from the signal. So this is something that we should not see that would occur within the data set because, yeah, it's just sort of a slow moving waveform. If we're trying to think about this physiologically, it's sweat being pumped out of these pores, which is like a slow process, being identified by the sensor as having more conductance or not, and then this sweat either being absorbed a little bit into the sensor or sort of reuptake back into that sweat gland. So this is again not a very rapid change sort of measure. So when we see these very sharp points here, this is something questionable for sure. So I'm gonna go into the editor to make a little bit of a change here. And so one thing is this occurs right at the end of the file. So just moving a little bit over using this hand tool can be helpful for us. And then what we can do is we can go back to our cursor tool here at the bottom. And I'm going to take the high sensor, so this, or the high cursor. This is identified here. You can see the change in the high X. It's also just the one that's to the right. So if I were to accidentally move this one to the left, onto the right side, it's now becomes the high. So in any sense, what we're going to do is we're going to move this over here. We do want to be very careful if we do have a skin conductance response that we don't extend from that point forward. So if you look, I'm actually picking this little shelf here. We could zoom in if we need to, but from that point forward, what I'm going to do is I'm going to say extend from that all the way over to the side. So what that's going to do is it's going to create that flat line from that point forward, and then extend it for the rest of that segment. And again, this is something that is normally fine for when we're looking at skin conductance level changes, but certainly something we want to be very careful about when we're looking at SCRs. Because if I had extended from that point forward, we wouldn't have a peak, thus we wouldn't have identified a trough, and we would have missed out on this sort of SCR here. So one sort of question that comes up when we do this kind of thing is, well, how do we know that this was the actual peak of that signal? It looks like it dropped out right away, but couldn't that have been the point at which the electrode came off is the point at which it's still rising. So then it kind of dropped off there. So this is a good sort of critique of this, and there isn't a great answer for it, right? If the sensor comes off, there's a lot of motion artifact, then we really don't know. So trying to keep this extending that I was talking about below 40% for a segment is helpful. But when we do see these changes here from quite a bit of range from 2.5 up to 8. There could be quite a bit of change by doing that extension. It's usually not that dramatic, but something to be aware about. And try to create some sort of standardization within your protocol so that we always know how much to extend by. And another technique would be also that if there's an SCR that is next to something like a motion artifact, we would go ahead and delete those points. So if you do want to take a little bit more of an aggressive approach to it, again, we do have a delete tool here. We can modify this by the mouse wheel, and we can actually say that we don't want to include that SCR just due to the sort of ambiguity of when that actual peak might have occurred. And then when we come back here, we can see that that's been successfully removed. Okay, so now I'm going to go ahead and I'll save my file here just for these data sets that everyone will get when I'm done. But I will go ahead and open up our next file and show a couple different techniques and examples that you might see. Okay, so in this one here, we don't have an edit file. So this is one in which we output this to that XLSX file. If we had made some edits or we want to continue on from that file, we want to say we have an existing one. This will have us load up that Excel file and we can go from there. But in this case here, so what we have is we have the electrodermal activity, aka skin conductance, aka GSR or GSC, has a lot of different names. But we will want to come along and simply select which one is the skin conductance, and then respiration here. So this is Likely respiration driven from a respiration belt, but we will want to make sure that's included. And if you have that respiration, and again, we do recommend it if possible, so we can differentiate the sort of psychological SCRs from the ones due to respirations. But if you don't have respiration, then our general recommendation is that you just look at skin conductance level changes. So, okay, so I've done that. Um, we do see I have events in the file here. So I'm going to go ahead and turn on these events. So one thing that's helpful for skin conductance when we're looking at these things, there's a lot of different ways we can look at it, but very specifically with event here, one thing we can do is we can set some sort of window such as -10. So that's 10 seconds before this event occurs. This is what you can think about as every one of these, right? This is being identified as an event. And then what we can do is look at 10 seconds after an event occurs as well. So I'm going to jump forward just to show you kind of what that looks like. So you can actually see here, this is the point at which it began, so there's not any time before it. But um, so right here, we can actually see that it's identifying this event that occurs here. There's another event that occurring here. So they're a little bit spread throughout the data set here. But our actual windows that we're looking at are going to be the 10 seconds before and 10 seconds afterwards. So we're actually getting those to look as, sort of an aggregate together. We can actually say split at event as well. So what this will do, again, this is before time here so much, but here is our first event and then 10 seconds afterwards. So we could look at something like the mean skin conductance right here that we see and the number of skin conductance responses, so the total count, or if it's event related or not. So if the event occurs here and we have that 1 to 3 second window, if that doesn't fall within there, then it's not going to be event related. So there is one that occurs afterwards, but the sort of latency from the event to that trough is less than a second. So this one is being counted as a non-specific SCR compared to if this trough was in that 1 to 3 second window over here, then it would be event related, for instance. So we can kind of come through here and we can see examples of what those events look like. But we can see that they're mostly non-specific until this occurs. So here's an event marker that occurs here, and then essentially about that 1 second minimum window, we see this trough, and there's the peak. So this is now being identified, this one here, as the event-related skin conductance response. Event, trough, at least second, and the peak. Okay, one more thing I do want to show within this data set here is just the calculation method that I talked about previously. So going to interval mode, we'll go ahead and look at this at something like a 1 second window to begin with, and I'm going to switch back to time. So in this case here, we see that a lot of these vertical bars that are breaking this data set up now into these sort of 1 second windows. And what we'll get from there is if we actually look at mean skin conductance, we have the interval 0. So this is actually the first one here. And what we can do is we can go from every one of these intervals and we can actually see the mean skin conductance as it changes through the 60 seconds, but in 1 second windows. So if we go through here, yeah, we're going to have a lot of these moving all the way through the entire data set. And not just as a visualization, so we can look while we're at this level. This is also output as a separate book that we'll essentially see, or a different page within that Excel file. So yeah, if we didn't want to make any sort of changes here, but we just want the output, then that's another way to get that done. When we actually look at the editor, if we needed to look at something closely, we don't see those events all over the screen. But yeah, just something else to look at. And again, we could look at this at something like 10-second windows, which can be helpful as well, and just see how the data is changing throughout the segment. So if we were to want to look at baseline here, and then all of a sudden they keep rising, this is helpful to know sort of when that rise actually might occur that we can see here. So sort of hanging out here around 31 and then jumping all the way up to 34 and staying at that point. So just another way to look at the data, if we should choose to do so. Okay, and now I'm going to go into my last data set for a few minutes here, and then we can open this up to Q&A. Okay, so in this data set here, once again, we have the electrothermal activity as GSC. We have this sort of just showing you all the different titles that one might choose for that. And in this case, we're actually collecting impedance cardiography along with skin conductance. Um, so what we're going to do is we're actually going to derive the respiration from that impedance signal. So instead of identifying as a respiration belt, we're simply going to mark the Z0, which is the raw impedance waveform, and its first mathematical derivative dz/dt. So if we do this here, then the software, if we go to the calibration settings, will automatically know to derive the respiration signal from Z0. Going back to the fact that this is a different file, we do always want to ensure, like, was this used the same acquisition device? So we can look at that sampling rate and just make sure that it's set to that same one. Of course, if we're looking at data that are collected from the same acquisition device for the entire study, we don't necessarily need to go and look at the sampling rate for each individual file, but it is helpful if we're looking at, let's say, different files from different systems. The sampling rate that is detected is output to the XLSX file, the Excel file I've been talking about. So if we wanted to look on the back end just to make sure that the rolling filter was set to the sampling frequency, you'll be able to look at that again in that Excel page. But okay, so I'm going to jump back into this file here and just show a couple different additional techniques and due to respiration. So as I talked about earlier, we have our event-related skin conductance responses. We have the non-specific. So in this case, I'm just sort of assuming that I don't have any events. I just went to time mode. So then all of them are going to be non-specific in this case because we don't have any events within the file. So they're all, like I said, non-specific here. But what we do want to look at is still, in addition to this, do we see any sort of respiration-driven skin conductance responses? Because if you remember correctly, like there is motion artifact, which again, these are these sort of slow-moving hills, these rolling hills. And if we saw the movement, we would see the sort of some sort of jagged structures along this, like we saw in the one of the first slides I presented that didn't have the rolling filter on. Um, and so then what we do want to look at, because those are a little bit more obvious to us, is the SCRs that could be driven from a respiration. So if we take, again, a deep breath, someone sneezes and then deep breath afterwards, or in some case they just take a quick breath in from startle, we can actually see that breath create its own SCR. And they look identical in a lot of cases to those psychologically driven ones. So one thing to look at here is we're looking for a respiration that really stands out compared to the other respirations within this segment. Um, something like on the order of 2 to 3 times the magnitude of everything else that we're seeing. So if we look at the entire trough to peak time, sort of the lowest point here, not skin conductance trough, but sort of the lowest point of this respiration signal to the peak here. Normally, if this is again like 2 to 3 times in amplitude, sort of the magnitude being 2 to 3 times the normal ones, then that's something we want to look at a little bit closer. So going into the edit, peaks and troughs, once again here, we can set one of our X cursors to the onset of that respiration. So it's going to be this first principal trough here on the yellow. And then we'll move this second one here over to when we think a respiration may have occurred that could have something to do with that corresponding SCR. So here's the onset of this very large respiration, and then I want to see, okay, here's this skin conductance response that occurs afterwards. So I'm going to put that trough location here, and I'm going to see if it's within that 1 to 3 second window. Because if I start to breathe here, and there's that 1 to 3 second latency period, this is theoretically the first point at which this skin conductance response could be correlated to the onset of this breath. So again, if we look at the time between these, we have 2.6 seconds, so that's well within that window of the 1 to 3. So in a lot of cases, what we'll want to do is delete the corresponding skin conductance response because it very likely could have something to do with this respiration. Again, this isn't a perfect science because this respiration could result in a very muted SCR, maybe not one of this amplitude. And so in such doing this, we certainly could be skewing the data a little bit to say that we have less skin conductance responses than normal, but this is sort of the best method currently available in which we can see that it's normally if we can keep iterator reliability and consistency in our editing, this perfectly fine structure to do, but there's certainly limitations in this approach. So um, take it as you will, and you can certainly create your own protocol and such, but this is the normal recommendation to remove those skin conductor responses due to respiration. Okay, so that is kind of the main component and presentation of everything. So we do have about 30 minutes here that we can open up to Q&A. I see that some of you have already asked questions, so I'm just going to really quickly review those, and then I'll start to answer these as we go along here. So one moment. Okay, so first one I see here is putting adult size skin dentist electrodes onto a child's hand, and how do I do that? So one thing you can do is if you want to reach out to us, we have a couple pictures, sort of demo pictures of how to put these sensors on their hands. Normally it's in the same location that we would have the adult ones. And what we're going to do is we're going to trim or cut the white sticky component of it and then place that on their hands, leaving that interior gel and metal clip intact. And then what we can do is just use a micropore tape or paper tape to ensure that that electrode, again, the gel and the actual metal clip portion, um, are adhering to the skin. So kind of just wrap it around the back of the hand, the front of the hand to make sure it's still connected to their hands. Because the part that we're cutting away is the adhesive component. So anyways, if someone needs to see specifically a picture of this and how this can be done, reach out to us and we'll send that along to you. Okay, I have a question here about the GSR signal being very fuzzy. So one thing to look at is just the range of the skin conductance, which can be helpful. So in this case here, we're seeing something around the 11 microsiemen level. So if we're seeing something very fuzzy, such as maybe something we saw in the first data set here, which I will load back up. So we could say that this signal looks very fuzzy here, or this one potentially before that. So just looking at the level to make sure that you're in the correct range. This isn't so bad, but if we get down to something like sub 2 microsiemens or down to that 0.5 microsiemens, this will degrade quite a bit more. So just keep an eye on that Y scale to make sure you're in that sort of normative range of which is about 2 to 20. And again, if it looks very fuzzy, normally it's the fact that you are below that range. It also could be the case that we didn't have any sort of rolling filter on, so I'm going to turn off my edit file, and I'm going to essentially turn this rolling filter off before, so you can see here that this degrades the signal quite a bit by not having any sort of rolling filter on. If we were to change this to something that might be improper for this device, again, sampling frequency 1,000. So what happens if we only do 100 on the same signal? It does seem more smoothed out than we saw before, but we're definitely seeing some of those high frequency and movement artifact changes that we don't want in the signal. Um, and so, yeah, again, this just sort of exemplifies the importance of using that rolling filter so that to make the data usable for analysis. And let me just review these questions one more second. Okay, so we have a question here about using conductance responses, and if they can be used in the absence of event markers. So again, the recommendation here was that we probably create just a count on the either, I mean, the total of SCRs. If you don't have any event files, then it's always going to be the total, and non-specific will be the same, of course. But if we just do a count of the amount of non-specific ones that occur under that period. So let's say that we had our baseline, which is, let's say, 300 seconds, 5 minutes. And then we have an actual condition, which is, let's say, 10 minutes. Um, what we can do is we can actually, look at how many of these non-specific SCRs occur within that 10-minute period and just report that cumulative total as as a metric there that we're looking at. So if you have some different stimuli, of course, that is repeated at random intervals within this condition, this becomes a little bit more challenging. But one thing, if you do have a video or even audio file that is synchronized with the physiology collection, then we can actually go back to the video and put in event markers manually of when these different conditions occur. So this is when baseline ended, or this is when the stimuli occurred. If it's on a screen, you can certainly do a screen recording, which can be loaded into our system here. So by doing additional settings, we can load up to 4 videos. If the video is desynchronized from the physiology, you can change that delay right here for every sample in the file. So this is a 1 kilohertz sampling rate here, so we can do every millisecond change and go through the data set. If this is data that you still have access to, but you're not going to have those event markers, one thing you can do to synchronize a video collection with the analysis after acquisition is have them create a motion artifact. So prior to baseline, have them actually touch the sensors on their hands. You'll see something like a very large motion artifact here. You can then look at the timing of when that occurred to the beginning of the video file. For instance, I'll go ahead and set this load to 0. And then we can see that this occurs 7.65 seconds into the file. So then we know that we can set that trigger of the video file to something like 7.6 delay. I think that's what it was off the top of my head. And then when we load that file, you'll have the set delay after that. Then the two should be synchronized. So this isn't an ideal way to do it. What we would normally do is have our acquisition software communicate and work with the audio video to make sure they're synchronized up front. But if you don't have that and this is the best you have, this is a nice way in which you can look at those and actually place those event markers in. So I'm not going to cover this too much here, but from this screen, we can actually we can export the events that we see here, or we can just export a template file. There's also manually creating event files. There's some MindWare support article, which you could look at. But essentially, if we can export these here, we will export to a text file. And I will go ahead and take a stab at that here. So we're going to look at relative time, so relative to the beginning of the acquisition. Absolute time, if you had time of day, if that's what the kind of realm you're working in, you can switch to that. But I'm just going to say relative for now. It has now output that data set into an event file here. And then, so we can see those different events that we saw before. And so essentially looking at that video or screenshot here of when those things occur here, we can come in. Again, this is a tab delimited text file, so everything's a tab in between, but we'll give it a title, such as, let's say that there was a cough or the onset of an event or something like that. We'll go ahead and give that a title of what kind of type it is. So let's say this is going to be coughs and sneezes. Okay, and then we're going to give it a title between each specific one. So this is essentially the group, cough, and then we can change the time to whatever that occurs within the video file. So something like this can work, and then we will save the file, and then we will essentially load it into analysis by saying add a minor event file. Once you do that, it'll add those events we just created and with the group here. So again, this is just another technique that we can use to load those events afterwards. This is a little bit of labor intensive if the videos aren't synchronized up front. So Just another technique that we can use to get those events in that we manually created. This can also be done in Biolab if you use MindWare to collect the device. We'll just open up the Biolab file after you've collected it, and then there's much easier visualization tools on how to implement those event markers there. Okay, we have a question here about the fact that this researcher does not have any respiration signals. So looking at the analysis of the non-specific SCRs is potentially not an option. But there's an additional question of clarifying the difference between skin conductance level and the mean skin conductance level. So mean skin conductance, what we would do there is if we had all these 60-second segments that are current within our file. Um, so I'm going to turn my segments down to 0 here. So what we're going to do is we're going to see the mean skin conductance for this specific segment here. And then what we would do for the normal mean is we would get these outputs for each segment within the Excel file. And then we're just going to, um, I'll go ahead and write these out so we can actually see what that looks like. Okay, and so yeah, I have connected that there. And now what I'm going to do is I'm going to go to the output data and I'll load it into Excel. And then from here, we can see that we have all the different segments here. Our mean skin conductance is tonic. So if we wanted to, we can just average across those 5 segments, and then we can get our mean for the entire data set. Okay, I think that is most of the questions we have here. So for everyone that has attended, I really appreciate everyone coming to this webinar here. If you have any additional questions, please send them along to us on our support site or through the various channels. And please remember to fill out your post-webinar survey. Okay, thank you, appreciate it, and hopefully everyone can join a future one.